Okay, so hi everybody. Thanks for listening in. So this is going to be a bit of a topic change from the previous few presentations. In this case, I'm not going to be talking about so much where objects are and how they move. We're going to talk about the light they produce or the light that they send to us. Light is a really important topic in astronomy because fundamentally most of these objects are so far away, we can only be studying them by remote sensing techniques. We can't take the piece of a distant star and do experiments on it in the lab. We are basically only able to look at them, which means look at the light they produce. There's a few cases where we can look at other things they produce, but we'll leave those aside. The fortunate thing is that the light from objects like galaxies and stars actually contains a lot of information. And we can use it to learn about the composition of these objects, their temperature, and even how fast they're moving. And so I want to spend a little bit of time talking about those subjects. Now, for this particular presentation, I'm going to focus on more fundamental aspects. And specifically, I want to start by focusing on what determines how much light we get from different objects, specifically stars, simply because those are nice, discrete objects that we can see a lot of. And the thing I want to emphasize right now is that the amount of light we get from stars depends on a couple of different things. It depends, first of all, on how close they are to us, whether they're close or far away. But they also depend on the physical properties of the star, their actual size and their temperature. And we'll talk about both of these aspects in the next little bit. This image is a good example of that because this is just a picture of part of the sky, and there's one particularly bright star right here with the reticle on top of it. That star is Sirius, the brightest star in the sky. And part of the reason it's bright is this star generates a lot of light. It actually produces 30 times the amount of light that our own sun does. But that's not the whole story, because it turns out there's another star in this image, this one here, which doesn't have nearly as nice a name. It's Nu 1 Canis Majoris, which actually produces just as much light as Sirius does. But it doesn't look it. It looks pretty faint. It's more like many of the other stars in this image. That difference arises because this star, Nu 1 Canis Majoris, is much, much further away. And distance between us and a source of light is an important aspect of how bright a star appears. Now, this shouldn't be too surprising to you. Just to take some examples from within the solar system. On Earth, we know the sun is fairly bright because don't look directly at the sun. The sun is a source of an immense amount of light and is fairly close to us, and so is responsible for daytime and all of that. But you could imagine if we got closer to the sun, say at the location of Mercury, which is actually only half the distance from the sun as Earth is, a little bit, or the sun would be even more intense, be even brighter. And for that reason, Mercury is quite a bit hotter than Earth. On the other hand, asteroids that are further away from the sun than Earth, they would perceive the sun to be fainter, and they are therefore somewhat colder. So this kind of trend should make sense. So the further you are from a source of light, the less of that light you see, is basically the idea here. But we can be a little more quantitative about that. The way to see that is to consider a situation like this. We have the sun, and I've erected gigantic spheres around it. One with a radius r, so r is just an arbitrary size, and one that's twice as big. Now, how would you do this? Don't worry about it. It's just here for illustration. What's useful about this picture is you can think of the sun as something that generates light. So there's light coming off the sun and going out into space. That light first passes through the inner sphere, then passes through the outer sphere. But the thing about light is space is empty, so that light doesn't go anywhere. That is, the light is never created or destroyed. It does move, but since light is not being absorbed, there's nothing to interact with it. The amount of light passing through the inner sphere and the outer sphere is the same. So you have just as much light passing through this inner sphere as the outer sphere. But that light is not distributed the same way. This inner sphere is smaller, so the light is more concentrated. There's more light coming through every little bit of area. By the time we go twice as far out, that same amount of light is spread over a larger area. So the amount of light going through any small patch of that area has gone down. That's basically what's going on here. Now, the thing to say is the area of this outer sphere is not just twice the area of the inner sphere, it's actually 4 times that. And that's because in addition to making the sphere twice as tall, we've also made the sphere twice as wide. That's a way to think about it. So what that actually means is that the brightness of an object, how bright it appears, falls off like 1 over the distance squared. Because as you go at greater distances, the light is spread over a larger area. This is illustrated in this little diagram. We start off with light going through a particular square. If it goes twice as far, it's now spread over an equivalent of 4 squares, 2 times 2. So the amount of light going through one of those squares is 1/4 of that. If we go out to 3 times the distance, we now have 9 squares that the light is being spread about. So a particular square only gets 1/9 of the light. So the amount of light entering a particular object, be it your eye or a telescope, falls off like 1 over distance squared, just like gravitational forces do. That's not entirely a coincidence, but explaining why those two things are the same would require way more than we can get into in this class. But 1 over distance squared is just how things work in a lot of different cases. So what that means is that the brightness of stars goes down very steeply with distance. If we have 2 identical stars, one at 100 light years from us and one at 200 light years from us, the brightness of this star is not reduced by a factor of 2 because it's further away. It's reduced by a factor of 4, which is a fair amount. The amount of light that we receive from a star is a steep function of how far away it is. And that is exactly why this star is so much fainter than Sirius, even though we think they produce the same amount of light. The thing is, we actually know the distances to both of these stars because we can measure that using parallax. Turns out Sirius is a very nearby star. It's only 9 light years away. It's the closest bright star to us. Nu-1 Canis Majoris, however, is 280 light years away. So it's actually 27 times further away than Sirius. Now, since it's 27 times further away, its brightness is reduced by 27 times 27, which is about 730, which is consistent with this star being about 750 times fainter than Sirius. And that's what we're seeing here. The many bright stars are stars that are close. Not all of them. There are differences in their intrinsic brightness. Sirius itself provides a good example of that. Sirius is what is called a binary star. It is not just one star, it's two stars in orbit around each other. There is Sirius A, which is a big bright star, and Sirius B, which is a much fainter star. Now, which you can see here, this light is from Sirius A, and there's a little dot of light down here, which is Sirius B. Now, the difference in the brightness of these two stars is not due to distance. Sirius B is actually in orbit around Sirius A. They're almost the same distance away. But Sirius A is 1,000 times brighter than Sirius B. So stars do also differ in the total amount of light they generate. And that arises due to their physical properties. Most importantly, their size and temperature. The size aspect is a little easier to understand. The total amount of light an object produces depends on how big it is. If you have a star that's emitting light from its surface, the amount of light, the total amount of light, something called luminosity, is basically given by how much area is of the star. And again, area scales like the square of a length scale, in this case, the diameter. If you have a star that is twice the diameter of another star, it has 4 times the area. And so it produces 4 times that amount of light. And indeed, Sirius B turns out to be a very small star. It is a white dwarf, a type of star we'll talk about. And in fact, you can use the ratio of the brightnesses of those two stars to get a sense of the relative size. But it's not quite that simple, because there's another factor that gets involved in this, which is temperature. The brightness of stars also depends on how hot they are. And this brings us into the other major thing I want to focus on, which is not just brightness, but color. Stars are not only differing in brightness, they also differ in what color they are. The classic example of this is in the Orion constellation. Here are the 3 stars in the belt. Here is Bellatrix, and here is Betelgeuse. What you'll see in this image, and what you can see with your own eyes, is that Bellatrix is actually fairly blue, while Betelgeuse is actually quite red. That difference in color actually reflects a difference in the temperature of these stars, how hot their surfaces appear to be, which also affects how much light they produce. And in fact, we can use those color differences to figure out something about their temperature. But if we want to do that, we need to start taking a deeper look into what color actually means. And we'll just start this today and talk more about it next week. Many of you have seen this, an image like this, where you shine white light onto a prism and it splits it out into different colors, red, green, and blue, for example. This is the familiar rainbow. What this image is supposed to remind you is that all these different colors are part of the same phenomenon. There is red light, there is reddish greenish light, yellow, greenish blue light, etc. There are different types of light with different colors, but they're all a manifestation of the same basic phenomenon. light is a form of what's called electromagnetic radiation, which turns out to not just include light, like we're used to, it also includes other, sometimes very surprising phenomena, like radio waves, infrared radiation, ultraviolet rays, X-rays. All of these are different types of electromagnetic radiation. And they're all connected to each other. Now, what do I mean by saying that they're electromagnetic waves? Well, what that comes down to is something that I think most people find very surprising, that electricity, like lightning, or the current running through your house, magnetism, like with magnets, and light are actually all interrelated phenomena. This is not obvious, and it took people a long time to figure this out. But they are related. It turns out that what light fundamentally is an oscillation that can be generated by the motion of charged particles, like the ones that make lightning, things like electrons, things like protons. If you take a charged particle, something like an electron or a proton, a subatomic particle, and shake it back and forth, shake it up and down, and you have another charged particle some distance away, that charged particle will start to oscillate up and down. And it will oscillate up and down at the same rate as this first charged particle. The way we understand that is that this oscillation produces a disturbance in the electric and magnetic fields that cause distant charges to move. Now, that disturbance has a couple of properties. The first is what's called its frequency. If you take a charge and move it up and down once every second, then the responding charge will also move up and down once every second. So this wave or oscillation traveling between the two also has that intrinsic frequency. Now you can shake it faster so that it goes through more oscillations per second, which is conventionally called a hertz. So if you shake it faster, you can go at 10 hertz, maybe you can go to 100 hertz. And you can also go slower. You could go at 0.1 hertz or 0.01 hertz. There's a continuum of possibilities for the frequency. So this light, this electromagnetic radiation that is going from one charge to the other has a characteristic frequency. It also has a wavelength, a spatial dimension. If this shows a bunch of dots indicating individual charges and how they would move in response to this oscillating charge. And there are places where the charges are being pulled up, and there are places where the charges are being pulled down. And they just repeat. And the two locations where the charges are moving the same way is a spatial scale called the wavelength. This is also the distance between two troughs, two places where it's being pulled down the most, two places where it's near the center, etc. There is also a length scale associated with this. And furthermore, there is kind of a speed associated with this. So if I take a charged particle and move it down and then move it back up, this creates an electromagnetic wave that then propagates to this other charge, causing it to move down and then up and then back. And the crests of this wave move from left to right as this wave propagates. It turns out the speed at which this wave propagates is independent of its wavelength or its frequency. It's just a constant of nature, and it's a conventional thing called the speed of light, which is indicated with the letter c. We'll get into what the numerical values are later. What this means is there's a relationship between wavelength and frequency. That is, if you increase the frequency, you necessarily reduce the wavelength of the light. So, for example, something with a wavelength of 1 centimeter, a type of electromagnetic radiation with that, has an intrinsic frequency of 30, what is called gigahertz. This is 30 times 10 to the 9 hertz. So fairly fast. If you cut the wavelength to a half, the frequency has to go up by a factor of 2. So if the wavelength is a half a centimeter, the frequency is 60 gigahertz. If the wavelength is a third of a centimeter, then the frequency is 3 times 30 or 90 gigahertz. So basically, frequency and wavelength are related to each other, and things that are higher frequency are shorter wavelength, and things that are longer wavelength are lower frequency. And you might say, why don't we just use wavelength or frequency? And that's a very good question, and it's because people are inconsistent. And so some people like wavelength and some people like frequency. And the thing is, the frequency of electromagnetic radiation can span a broad range. It can range from tiny to huge. This is a plot showing the different types of electromagnetic radiation as a function of frequency along this and wavelength along the bottom. And what you can see here is the range. The frequency goes from 10 to the 0 for 1 hertz all the way up to 10 to the 24, or again, 1 followed by 24 zeros hertz. The wavelength can go from 10 to the 8 meters, which is many, many kilometers, which is like 100,000 kilometers, all the way down to 10 to the minus 16 meters. So the scale of atoms. These are all the same type of electromagnetic oscillations, but they're given different names because they interact with matter so differently. Now, the ones we're most familiar with is visible light, which is right here, which has wavelengths of around 500 to 700 nanometers, which is roughly the width of a human hair, give or take. But we have types of electromagnetic radiation on either side of that. If we go to longer wavelengths or lower frequencies, we enter the realm of infrared radiation, IR. Infrared, less than red, so lower frequency. Then this extends from roughly 1,000 nanometers, so very red light, all the way to basically a millimeter of wavelength. Then we transition to something called microwaves. Now, these aren't microwave ovens. They're a type of electromagnetic radiation that's sometimes kind of used in microwave ovens, but also in cell phones, etc. These are between a millimeter and a meter. Once we get up to a meter, we end up in the realm of radio waves, things like FM and AM radio, other types of communication, signals we get from power lines, etc. So all of these are different types of long wavelength radiation. On the other side, we have short wavelength radiation. Beyond, at higher frequencies and shorter wavelengths, we first enter the world of ultraviolet. So above violet, again, applying to the frequency. Again, red is long wavelength radiation, blue is short wavelength, ultraviolet is even shorter. It goes down from, 400 nanometers down to about 10 nanometers. And once we go beyond ultraviolet radiation, we enter the world of X-rays. And yes, this means doctor's X-rays. Those are a type of electromagnetic radiation that are even higher frequency and shorter wavelength. And as we go beyond that, we enter the realm of what are called gamma rays, which are the highest frequency, lowest wavelength things, and they have these short wavelengths. Now, these are all the same basic type of phenomenon, but they interact with matter in fundamentally different ways because of their different wavelengths. The radio waves, these things are long wavelengths, so they interact with matter on large scales. Thus, you have the ability to push around a large number of charges relatively smoothly. This is why they're used for light communication, because they can drive the currents in an antenna. For things in the ultraviolet to infrared, which include visible light, the way they interact with matter starts to change. It becomes much more about interacting with individual molecules or atoms in a material. This is why everything appears different colors to you. Different materials have different atoms and molecules, and those interact in different ways at these wavelengths. But if we go to even shorter wavelengths and even faster frequencies, we're now shaking the charges so fast, you can tear apart atoms. And often you do. This is why this type of electromagnetic radiation is often more called radiation. It is damaging to atoms, molecules, etc. And this all is relevant for understanding color, because these different types of electromagnetic radiation is produced by a variety of different processes. Some of those processes are distinct to particular wavelengths. Others of them are general. And the one I'm going to focus on first, which I'll talk about next week, is what's called thermal radiation. It's a type of radiation due to the fact that something's at a finite temperature. And it turns out that has a very general form. And by understanding that type of radiation, we can understand why Betelgeuse is red while Bellatrix is blue. So, but again, thank you for your time and attention, and I'll see you next time.